Good morning, students. Today we are going to discuss the combinations of capacitors. We have already done the introduction to this topic, combinations of capacitors. And one typical combination that has appeared in the exam, it is a capacitor like this connected to two other capacitors which are parallel to each other, but they are in series with this capacitor. Let's label them as X, Y, and Z. There are three capacitors. If each capacitor is clearly labeled as 30 microfarad, 6 volt. This is labeled, each capacitor is labeled with these two figures. That simply means that the capacitance of each capacitor is given to be 30 microfarad and the maximum voltage that we can apply across this should be 6 volt. That simply means that we can charge each capacitor to the maximum voltage of 6 volt. That of course will be the maximum about how much charge we can store on it or how much energy we can store on that device. So usually these two numbers are written on it. For this particular combination now, the one usual question they ask is, what should be the maximum voltage of the battery that we can connect across this combination? If I connect a battery at the points A and B, what should be the maximum voltage across these points A and B? Now let's say we connect a battery like this, and keeping this information in view, what should be the maximum voltage of this battery? If I simplify this picture, this is 30 microfarad and these two together have a capacitance equal to 60 microfarad. Because one thing that you need to remember is that when capacitors are connected in parallel, their capacitance is added. So for parallel combination, the capacitors are, if they are in series, let me write this formula here so you remember. For series combination, 1 over C total is equal to 1 over C1 plus 1 over C2. This is how we calculate the total capacitance of any number of capacitors connected in series. But for parallel combination, C total is C1 plus C2. So these are two simple formulas that you will remember. Yesterday we did discuss the charge and the energy stored and quite a few other things, but this is something we need to add to that detail, that if we have a series combination of capacitors, then the total capacitance is calculated in this manner. We take the reciprocal of each capacitor, we add them, and what we get is the reciprocal of the total capacitance. This is something we used to do with the parallel resistors, and this is something we used to do with the resistors in series. But now what we did for parallel resistors, we are doing for capacitors connected in series, and what we used to do for series combination of resistors, we are doing that for a parallel combination of capacitors. So you need to understand this. So if the two capacitors are connected in parallel, I am adding their capacitance, so the total is 60 microfarad. And now that I know the two capacitance, I can guess what should be the maximum value of allowed voltage if I know one more point, and that is if the maximum voltage across this capacitor is 6 volt, because this is known to be 6 volt. This is the single capacitor connected in this, and the maximum voltage allowed across this should be 6. So if we have 6 across this, what should remain across this? If I have a certain voltage here, the maximum, since maximum is 6 allowed across this, and this is 2 times the, this is twice as much the capacitance of this, the voltage across this should be half as much. This should be 3 volt. So the point is, if capacitance is twice as much, the voltage drop is half as much. The opposite is, if capacitance is half as much, the voltage is twice as much. So it is the opposite relationship, because clearly they are connected in series for the same Q. C, this is Q is equal to CV. That means if you increase the capacitance, you decrease the voltage if it is in the series combination. For the same charge, if C goes up by a certain factor, V goes down by the same factor. So this is something we observe in this example. If capacitance is double here, it goes up by a factor of 2. The voltage drop, it goes up, the capacitance is going up by a factor of 2. The voltage across this is going down by a factor of 2. So this is for the series combination, because this is something that remains constant on each plate when we are connected them in series. So one part is done. Now, if I know that I have the voltage across this is 6 volt now, this is 6 volt, and its capacitance is also known 30 microfarad. What should be the charge stored on this plate of capacitor X? Charge on each plate of capacitor X. Obviously, this will be Q is equal to CV, and therefore it is C, which is 30 microfarad multiplied by 6 volt. So this is 180 microcoulomb of charge that we can store on each plate of it. What should be the charge on each plate? Charge on each plate of Y, this capacitor. What charge do we expect here? Because we know the total charge on this combination will be same as this, because the two are in series, but that total charge will be divided because the two capacitors are in parallel. So this 180 microcoulomb charge will be divided exactly into 2 because the capacitors are identical. So 90 microcoulomb will be stored on this and 90 on this. Each plate of these capacitors will take. So even if our calculations show Q is equal to C, the total is 60 into 10 to the power minus 6 because the capacitors are in parallel, the capacitance being added. So 60 microfarad multiplied by 3. So again 180 microcoulomb is the total charge on this combination, all this, because 3 is the total voltage across this and 60 is the total of this. But by dividing it by 2, this is 2. So this gives us 90 microcoulomb of charge on each capacitor Y and Z. What is the energy? What is the total capacitance of this combination, and what is the total energy stored by this combination? The total capacitance, although I have done the total of these two, but what is further simplification possible is that if I know this is 30 microfarad, I know this is 60 microfarad, after I add them, this is a series combination. What is the total capacitance of these two capacitors combined if I make them into a single capacitor? This is done by 1 over 30 plus 1 over 60. So when I simplify it, I get 1 over 20. So that means the total capacitance is 20 microfarad. So 20 microfarad is the total capacitance of these two, because this is the total, this one. C total is 1 over C1 and this is 1 over C2. So 20 microfarad. So if I know it's 20 microfarad and I know it is 9 volt connected across this capacitor, which is now reduced to a single value of 20 microfarad. This is 9 volt battery. So the total energy stored is equal to 1 over 2 CV square. So this is the formula that we have already learned. I know the capacitance now, which is 20 microfarad, and I know V, which is 9 applied across this. So use these numbers. Simply, they give us how much energy this combination of capacitor is now storing. So this is about the combinations, the series and parallel combinations of capacitors. And usually this is the maximum level of difficulty that we have in the questions. If you go through the past paper questions, you have a few more questions of this type. You can try some of them on your own. Sometimes they talk about spherical capacitors, and one capacitor is already charged. It has a certain capacity, certain capacitance, and certain value of potential to which it is charged. Then another spherical capacitor is brought close to it and they touch each other. Then what happens to this combination of capacitors? What happens to the energy stored? And what happens to the charge? This is also about the combinations of capacitors, but for spherical capacitors. I have selected one question from the past papers, and that is the only one which has appeared in recent past papers. In this question, they have informed us that a certain capacitor is given a charge and the value of potential is given, its capacitance is given. This has capacitance equal to 6.5 picofarad and the voltage to which it is charged is 220 volt. A few simple things they ask us to calculate include the radius of this spherical capacitor. A radius can be calculated using the simple formula that we learned in the last lesson, in our previous lessons, in which capacitance was related to the radius of a spherical capacitor. If you remember, it was C is equal to 4 pi epsilon naught times the radius of the spherical capacitor. So this is the formula that you will always use in order to calculate the radius if you know the capacitance of a capacitor. So in this case, since we know this and we know the value of epsilon naught in the data booklet that is given, using these values we can work out the radius to be 6.1 into 10 raised to the power minus 2 meter. And if they ask us to calculate how much charge it has stored, how much charge, since I know the value of capacitance and I know the voltage to which it has been charged to, I can multiply these two values. Q is equal to CV. So this is 6.8 into 10 raised to the power minus 12 times 220. This gives me the charge which is 1.5 nanocoulomb of charge stored on it. But this has nothing to do with the combinations that we are talking about. This is just the spherical capacitor with its usual properties, the voltage to which it is charged, its capacitance, its radius, and the charge we can store on it. But the important point comes next. When we touch this capacitor, this spherical capacitor with another one, which might be of different dimensions, they have not informed us, but when we touch these two things definitely change. One thing that changes is the total voltage now, because the charge is shared on the two, so potential of the surface is not the same now. It has definitely going to have a smaller value now, because if you have a bigger surface now with the same charge shared on it, that is a smaller value of potential. So one thing is definitely going to be different. The other thing which is going to be different is now the capacitance of this combination, because we have now a larger surface involved. Instead of one sphere, we have two spheres side by side. So we can store larger amount of charge on it. So capacitance is going to have a larger value that we can work out. So we can store more charge on this surface. We can raise it to a still higher value of potential, because previously it was 220 volts. After the two spheres touch, the potential on the surface goes down because of the sharing of the charge. So a few calculations they have asked us to do is, what is the new value of potential now? If another potential, and they are probably assuming, although there is no direct hint about this, maybe in the statement of the question there is some hint. If another sphere is brought close to it and is touched with this, the charge is shared, the new potential can be calculated with the help of these values. Since I know the total charge stored on it was, the total charge stored on this, we just calculated, it was 1.5 nano coulomb of charge. One hint that must be provided in it is the new capacitance, because this is 6.8 picofarad. Now its capacitance must have gone up by a certain value, and that is to be provided in the statement of the question. The new capacitance, new value of capacitance must be provided. Let me assume it is something like 8 picofarad. So if I know this is 8 picofarad, what should be the new potential? New potential. So C is equal to, or using Q is equal to CV. If I know this to be 8 picofarad, 8 into 10 to the power minus 12, V is to be found, and this is 1.5 into 10 to the power minus 9. So with these numbers given, I can easily work out the value of new potential now. And my calculations are showing a different number because I have not noted this number from the statement of the question. But anyway, this is how you can use the formula if the new value of capacitance is given, because they have the two capacitors have now come close and they have touched. So capacitance is different. With this capacitance, charge has not gone away. Charge is simply shared on the two. So the same value of charge is used. So maybe instead of using same charge is used and the new capacitance is used, and the new value of potential is quickly worked out. And once you know the value of potential calculated from this equation, you can also calculate the change in energy. Change in energy stored on the two. For this purpose, we can use two formulas. Either you can calculate the capacitance, you can use this capacitance and write 1 over 2 C1 V1 square, and then you minus the second two values with the same formula C2 V2 square. This is possible. But an even more convenient formula would be, let me write it here. A more convenient formula would be 1 over 2 Q delta V, because Q has not changed in it. So no need to write different values of capacitance and voltages. You just have to write the same value of charge, which in this case was 1.5 into 10 to the power minus 9. And this is the two different values of potentials that you calculated from this given information. The value you have in the beginning and the one you have calculated later. You take the difference of the two and you multiply this. This is the change in energy stored. So this is delta E, let's say, that you are calculating. So this is all for today. We'll discuss, probably we'll continue discussing a few more questions for practice. And if there is not much In tomorrow's we can start a new topic. Thank you for today.